Okay, this is reliability. In reliability, I'll do it a little differently. I'll be mostly focus on showing you the concept rather than doing Excel because there's not much Excel you need in this particular chapter. Okay, so reliability. What's a reliability? This is a likelihood or probability of a certain service delivery system or product keep up and running within a given amount of time. Okay, so let's say if the system has a reliability of 80%, that means 80% per year. That basically means within a given year, about 80% of the time, that machine or system is functioning just fine. Okay. So in reliability, in order to understand the reliability of a system, largely you need to understand two fundamental forms of system design. Okay, first the design is this particular design you are seeing, and next design is this particular design you are seeing here. Okay, I'll explain this one by one. So the characteristics of the first system, this first type of system is also being referred to as a series design. Okay, in this particular design, I think as you can see that in order for this system to functioning normally or being reliable, both component has to work. Okay, so that means given A is working, component B should also be working in order for this particular system to deliver whatever it is intended to deliver. Okay, so in this case, how do you understand the reliability of the entire system, not just one component by component? Okay, so I will use a little tool called a tree diagram to show you how to understand this concept. Okay, so there is a chance that A is functioning just fine. We know that this percentage is 95%. So out of let's say every 100 day, in 95 days, A is just working just fine. Okay, but there are also 5 days in every 100 day that this is not functioning. It's not reliable. It doesn't work on those 5 days in every 100 day. So there are two different scenarios. Okay, so given A is functioning fine, there's a chance that B is also functioning fine here. Okay, let me just draw it like this. B is also functioning fine. Okay, because B is up and running in 89% of the time, but there is a case where but A is working, B is not working. The chance that B is not working is is basically 1 minus 98%. Okay. Given A is not working, there's also two scenarios that can happen to B. It's just B is working, and this percentage is 98%, and there's a chance that B is not working. That we know that this chance is 2%. So now we have like 4 different type of scenarios for this little simple 2-component system. And A is working, and B is also working. This case, the system won't function. The system will function. A is working, but B is not working. Obviously, in this case, system is not working. And A is not working, B is working, the system is also not working, and A is not working, and then B is not working. So in all 4 different scenarios, I think that what we want to know specifically, because we wanted to know the reliability of the system, if you break down that statement, that's basically when both A and B are working. Given A is working, B is also working. And unfortunately, all 4 at the below will have at least one that is not working. So therefore, we don't need to consider that. Okay. So to calculate the reliability of A and B, just follow this particular diagram. You are multiplying reliability of A with reliability of B. Okay. I know that those 3's are ruled out here, but if you really want to know what's the chance that A is working but B is not working, given A is working but B is working, okay, given A is not working, which is 5%, and B is working, and given A is not working, B is also not working. Those are. So all three of them will be relevant in next scenario, but is not relevant in this scenario. So in order to understand the reliability of A-B series system, you're basically multiplying 95 with 98%. That will give you. So intuition here is when this is a series system, this is not a very, very reliable design, because whatever component that comes after initial component, you'll basically keep discounting the reliability of the very initial component, okay? Because no component will be 100% reliable. Therefore, you're looking at a probability that is less than 1. Therefore, that's what I'm saying. The more component that you add, the less reliable the entire system is going to be. Okay, if you think about a teamwork situation where you have to pass down your work to next person, we'll say for you define reliability as delivering it to before the deadline, and I mean everybody has their own reliability number, let's say, and because you keep passing it down, you may not be 100% reliable, and your next person may not be 100% reliable, and next person may not be 100% reliable, and the more people you add to the team, if the work is done linearly like this one, the resulting reliability will be significantly discounted. That's the case here. Okay, so long story short, what's the answer here? 95%. Oops, 5% multiply 98%. So you'll be getting reliability of 0.931 in this particular case. So this number is not greater than any of those two numbers you've seen here. So this is reliability in series. So what's the meaning of this formula? This weird symbol is a pi symbol, meaning that you basically have to multiply all the numbers in the set. Okay, so this is easier version. So if this is more easier for you to understand, you can just take that version. Okay, so you keep multiplying all the reliabilities one after another if this is a series system. And the result is that you will be seeing a result is that most likely you will see a number that is smaller than most of reliability numbers you see from each component individually. Okay, then let's talk about the next system design. This is a parallel system, or in some cases this is also being referred to as a backup system. Okay, so I think your textbook is referring to this as a parallel redundancy or either backup. Those are all somewhat similar. The idea here is that as long as one is up and running, the entire system is working. Think about that. That's the definition of backup, right? If you have one backup, that means if the original one died or not reliable, and then the other one will jump in and makes the system still very, very reliable. So that's basically the story here. So going back to this original illustration here, okay, because this is the same A-B component with exact same amount of the exact same value for the reliability. The definition wise, for a backup or parallel, you need to ensure at least one is up and running. At least one is up and running. So if you look at this, if you look at the whole thing, so this scenario is considered just fine. This scenario is also considered just fine. This scenario is also just considered just fine. Okay, it's just only this particular scenario is a scenario that we need to rule out in order to calculate the reliability of a system with a backup. Okay, so calculation-wise, what does that mean? Calculation-wise, it's simple. So you need to do that 1 minus probability of failure for A multiplied by the probability of failure for B. Okay, so you're basically ruling out only this particular scenario, and then you are calculating probability for all those scenarios. Okay, so I mean all those scenario basically means 1 minus this particular scenario, because all 4 scenarios combined will have to be equal to 1. Okay, so for the parallel system, your probability is keep up and running, or the reliability is, okay, let me see, 1 minus 0.05 5 multiply 0.02. It's going to be 0.99. Okay, so as you can see that in this design, our reliability is fairly high at 999%. It's higher than any of those numbers. Okay, this is because we're using a backup design or parallel design that as long as one is working, the whole thing is working. Okay, so in this case, the simple to remember formula is basically 1 minus cases where everything is not functioning. I know that your textbook is using slightly more complicated equation, but I think to most of us, this way of calculating the reliability of a system with a backup is going to be more intuitive. 1 minus chance that everyone is not working. Everyone is not working. Allow me to just remind you several examples from your textbook. So this is a fairly simple, okay? This is a fairly simple design. You need to recognize what design each problem is basically asking you to solve. So this is very simple. This is a series system. So your reliability is basically defined as R1 times R2 times R3. So you keep multiplying those numbers, right? Multiplying those numbers, you'll be getting 0.713. As I mentioned earlier, if this is a series system, your resulting reliability of the system will most likely be smaller than the rest of all the components, their individual reliabilities. Okay, and the next one is the reliability with a backup. Okay, so in this case, R1, R2, R3, at the highest level, there's still a series system. However, you're adding one backup to R1, exactly same component with the same amount of reliability, and R2 you're adding the same component with the same amount of reliability, and they're becoming backup. Okay, so for this type of problem, even though that looks so complicated, you just need to do it one at a time. Okay, so because overall you're looking at overall because you're looking at a series system with R1 and with R2 and with R3. Okay, because this is your overall design, so you just have to figure out what is the reliability of R1 first and R2 next and then R3. So why do you need to figure out the reliability of R1? Because R1 is no longer just R1 one component. This is a component with a backup. Therefore, you need to think about this case. Okay, you need to think about the case where there is. You need to think about the case where at least one of those two components, one being backup, one being the original, is working. So the way I will calculate for R1 is this is 1 minus. Let's say R1 is equal to 1 minus. 1 minus 90%, because this is a chance that R1 will be failure, and another 1 minus 90, this is a chance that R1 is also going to go failure, and therefore you'll be getting 1 minus 0.10 times 0.10, multiply it. So let's see, it's going to be 1 minus 0.10 times 0.10 is equal to 99%. So by adding a backup, reliability of R1 has shot up to 99%. Okay, so you got 99% here, and in the same way, you can calculate the reliability of R2 as a component with a backup. So it's going to be 1 minus the chance of failure is going to be 0.2 multiplied by the chance of failure for its backup. So you're getting 0.96 here, and then you multiply R3 as is, which is the one without any backup. Okay, so here, those are three numbers you need to multiply. Eventually, you'll be getting 94 as a reliability. So the textbook has solved it a little different way. I mean, if you're willing to take a look at the way textbook has calculated, if that is more intuitive to you, more than welcome to use that. But I think that most people will find that ruling out chance that all of them are failure will be, I think, more intuitive. And lastly, this is a reliability with a parallel redundancy. So in this particular case, it's basically the same, even though looks very complicated, it's still that as long as any one layer in this particular parallel system is working, the entire system will be working. This is essentially a, backup in different appearances. Okay, so here, if you are confused how to do this thing, okay, so if you look at this, you need to, decompose to smaller pieces and digest one at a time. So R1 by itself, and then you have R2 and R3 are the middle layers. Okay, this is a subcomponent inside, subsystem here. This is a parallel system. Okay, and then R4 itself. So eventually you'll be reducing this to R1 and R2 and 3 combined, and R4, R4 here, and then they will be somewhat, in this type of backup appearances. Sorry, I'm poor in drawing. So the key here is, of course, you need to calculate R2 and 3 combined system first. This is obviously a series system, so it's going to be 0.975 times 0.975. Okay, so you will get something like 9506 because it has calculated already. Okay, this is it, and then it will simplify into like sort of like a R1 with the R2, 3, and R4 as a backup. So as long as any one of those are working, the system is considered working. Therefore, what you need to do is 1 minus reliability of R1, which is 95%, and multiply by reliability of R2, 3 minus 9506. Minus 1 minus 95%, which is reliability for R4. So this, when calculated, according to our book, is going to be 0.00012, and resulting reliability is going to be 999.99988. This is 9. Okay, so really key is you need to know which part of the system you need to simplify first, and then the system that you intended to simplify, whether that is a parallel or series. Okay, in next video I'll be giving you more examples, so you're more than welcome to try by yourself at this point, but if you need more examples, more than welcome to watch next one.